Atmospheric pressure plays a key role in bullet trajectory because it directly influences air density, which in turn affects the aerodynamic drag experienced by the projectile in flight. At higher atmospheric pressure such as at sea level or in dense weather conditions, the air is thicker and more resistant, increasing drag force on the bullet. This causes the bullet to decelerate more rapidly, leading to a steeper drop over distance due to gravity's constant pull. Essentially, the bullet has less forward momentum to fight against downward acceleration. Conversely, lower pressure like at high altitudes or in thin air reduces drag, allowing the bullet to maintain velocity longer and travel on a flatter trajectory with less drop. Snipers account for this by using tools like Kestrel meters to measure barometric pressure, temperature, and humidity, then applying ballistic calculations e.g. via apps or dope charts to adjust their aim, often elevating the muzzle slightly more in high-pressure scenarios to compensate for the increased drop. For instance, a .308 Winchester round might see a trajectory difference of several inches at 500 meters between sea level pressure about 29.92 in Hg and high altitude conditions around 25 in Hg, potentially turning a hit into a miss if ignored. This relationship is rooted in the drag equation: drag force equals 1 to air density velocity superscript 2 drag coefficient cross-sectional area, where air density ρ equals PRT, with P being pressure, R the gas constant, and T temperature. Buildings in urban environments create complex wind patterns through a phenomenon known as the urban canyon effect, where tall structures channel and accelerate airflow like wind tunnels, often resulting in swirling eddies, downdrafts, and unpredictable gusts that can deviate a bullet's path significantly over distance. For snipers, this means wind speed and direction can change dramatically within short spans, calm at street level but turbulent at higher elevations due to buildings funneling air upward or creating vortices around corners. For example, a crosswind might shift from 5 miles per hour to 15 miles per hour in a matter of meters, imparting lateral drift via the Magnus effect, where the bullet's spin interacts with uneven airflow to curve its trajectory left or right. To compensate, snipers use tools like anemometers or observe environmental indicators such as flags, smoke, or mirage distortions in their scopes, then apply hold-offs or Kentucky windage, adjusting aim points based on calculated deflection, often using formulas like drift equals wind speed time of flight sin wind angle constant, where time of flight is derived from ballistic tables for the round's velocity and range. In practice, a .338 Lapua Magnum at 800 meters might experience 2 to 3 feet of wind-induced drift in a steady 10 miles per hour crosswind, but urban turbulence could double that variability, demanding constant reassessment and potentially multiple spotter inputs to ensure precision hits amid the chaos. Windage and elevation adjustments are critical corrections snipers make to their rifle scopes to compensate for environmental factors affecting bullet trajectory, ensuring precise hits at long ranges. Windage refers to horizontal adjustments for crosswinds, which push the bullet sideways via the Magnus effect, the spin-stabilized projectile interacting with airflow to create lateral drift. For instance, a 10 miles per hour right-to-left wind at 800 meters might require a left 2 minutes hold, where 1 minute of angle, or MOA, equals about 1 inch per 100 yards, shifting the point of aim right to counteract the leftward push. Elevation handles vertical compensation for bullet drop due to gravity, air density, and range. Bullets follow a parabolic arc, so for an 800-meter shot with a .308 Winchester, you might dial up 3 clicks, each click typically 0.25 MOA to raise the muzzle angle, accounting for roughly 20 to 30 feet of drop without adjustment. These are calculated using ballistic tables, apps, or experience, incorporating variables like muzzle velocity e.g. 2800 fps, ballistic coefficient 0.4 to 0.5 for typical rounds, and site-specific data from tools like rangefinders and anemometers. Miscalculations can result in misses by feet, turning a center mass hit into a graze or complete failure, especially in dynamic scenarios where spotters provide real-time calls to refine the shooter's dope data on previous engagements. Temperature significantly impacts bullet trajectory through its effects on air density, powder burn rates, and barrel harmonics, all of which alter the projectile's velocity, stability, and path. In cold conditions, e.g. below freezing, air becomes denser, increasing aerodynamic drag similar to high atmospheric pressure, which slows the bullet faster and exaggerates drop over distance, requiring snipers to adjust elevation upward, perhaps by several MOA at long ranges. For instance, a .338 LPU round that drops 10 feet at 1000 meters in 70 degrees Fahrenheit might drop an additional 1 to 2 feet in 20 degrees Fahrenheit due to the thicker air resisting forward motion more. Conversely, warmer temperatures thin the air, reducing drag for a flatter trajectory but potentially causing inconsistent powder ignition if ammo isn't temperature stabilized, leading to velocity variations of 10 to 20 fps per degree change, which at 800 meters could shift impact by inches. Internal ballistics also play a role. Cold ammo and rifles contract slightly, potentially tightening tolerances for better accuracy in some setups, but extreme cold can make propellants burn slower, dropping muzzle velocity by 50 to 100 fps, necessitating holdover compensations via ballistic calculators that factor in temperature alongside humidity and pressure. Snipers mitigate this by using tools like chronographs to measure actual velocities in current conditions, then updating their dope charts, ensuring that in a 12 km movement to an intercept point, they preposition with environment-specific data to maintain precision when the shot window opens, as even small thermal shifts can turn a hit into a miss in high-stakes scenarios. Leading a moving target in sniping involves calculating the precise amount of lead or offset aim ahead of the target's current position to account for its velocity and the bullet's time of flight, ensuring the projectile intersects the target's path at the exact moment of arrival, essentially solving a dynamic intercept problem rooted in relative motion. For a vehicle traveling at speed v perpendicular to the line of sight at range r, the lead distance dvr muzzle velocity, where time of flight is approximated as r muzzle velocity, typically 2500 to 3000 fps for sniper rounds, but refined with ballistic tables or apps that factor in drag-induced slowdown. For example, at 847 meters with a .308 Winchester muzzle velocity 2700 fps, time of flight might be about 1 second, so a vehicle at 30 miles per hour 44 fps requires leading by roughly 44 feet. Translated to angular mil or MOA holds e.g. 1.5 mils at that range. Snipers adjust for angle if the target is crossing at a diagonal, lead reduces by sin bearing angle plus wind drift, Coriolis effect for extreme ranges, and vehicle acceleration deceleration like slowing for curves, often using mil-dot reticles for quick measurements and spotter calls to dial in real time. Misjudging by even 0.1 seconds can miss by feet, turning a center mass hit into a graze or failure, demanding practice on moving ranges to build intuitive compensation under stress. Shooting at angles, such as from a ridgeline overlooking a target below or uphill, requires snipers to compensate for the reduced effect of gravity on the bullet's trajectory compared to flat ground shooting, using the rifleman's rule or cosine adjustment to avoid high hits. When firing downhill or uphill, the true gravitational drop is based only on the horizontal distance to the target, not the slant range measured by a laser rangefinder. For example, at a 30-degree downward angle and 900-meter slant range, the horizontal distance is 900 cos 30 degrees 779 meters, so you dial elevation as if shooting at 779 meters flat, preventing the bullet from impacting 2 to 3 feet high due to less drop time. This is calculated via tools like angle cosine indicators ACI mounted on the rifle, which measure the angle theta, then multiply the slant range by cos theta for the adjusted range input into ballistic solvers, accounting for the fact that gravity pulls perpendicular to the Earth's surface, not along the line of sight, with errors compounding at steeper angles, e.g. 45 degrees halves the effective range for drop. Without this, a .300 Win Mag at 45 degrees and 500 meters slant might strike 10 to 15 inches high, turning a vital hit into a miss or wound. Snipers practice this on inclined ranges to build dope charts, ensuring precision in mountainous or urban overwatch scenarios where angles are common.